Hello, in this presentation, we will introduce our paper titled Adaptive Non-Uniform Time-Step Sampling for Accelerating Diffusion Model Training. We offer a hypothesis explaining why non-uniform training strategies may offer advantages over the conventional uniform training approach. We begin by assuming an independent parameterization across diffusion time steps with the independent set of parameters for each time step. This parameterization allows us to have independent optimization objective per time step. We now have divided the problem into T independent subproblems LT, where the training with uniform time step sampling corresponds to uniformly selecting one of these subproblems and performing a stochastic gradient step on each corresponding parameter. Informally, if certain subproblems are particularly more challenging and require more iterations to optimize, there is a potential for improvement through non-uniform training strategies. In this sense, we assess the difficulty of these subproblems by measuring a variance of stochastic gradient. Theorem 1 implies that the number of iterations needed for SGD to converge increases in proportion to the gradient variance. Considering that the gradient variance at each time step reflects the difficulty of the optimization problem at that specific time step, we present the measured gradient variance during diffusion model training in the top row of the following figure. The results clearly indicate an imbalance in gradient variance across time steps. Notably, for R3 schedules, the gradient variances at early time steps are significantly higher than those at later time steps, and this trend persists without fading quickly. Since the variance at optimal parameters serves as a lower bound on the number of gradient iterations required for convergence, we anticipate that the early time step might pose a bottleneck to training efficiency when time steps are sampled uniformly. These results suggest that oversampling early time steps and undersampling later time steps could enhance overall training efficiency by effectively addressing the bottleneck presented by the subproblems at early time steps. However, without the assumption of independence across subproblems LT based on specific parameterization, the optimality of such a sampler is not guaranteed. The following figure illustrates the extent of interdependence among subproblems during diffusion model training. The figure reveals that the loss increase in untrained time steps is significantly greater than the loss reduction in the trained time steps, highlighting the strong interdependence between subproblems. Given that gradient variance can differ by up to 100-fold, it is evident that sampling in proportion to the gradient variance alone would likely be insufficient to effectively reduce the loss at later time steps. Through experiment, we confirmed that sampling time steps in proportional to gradient variance yields poor performance compared to our approach. Building on the need for non-uniform time step sampling scheme discussed in the previous slides, this section introduces an adaptive time step sampler Pi designed to enhance the training efficiency of diffusion models. We present a method for jointly training this sampler with the diffusion model in an online manner. Our goal is to train the time step sampler Pi phi to minimize the original objective, the variational low bound LBLB, as effectively as possible within a finite number of training time steps. To achieve this, we seek to optimize the sampler pi phi to sample time steps t that yield the greatest reduction of LVLB at each iteration k. Following an update from theta k to theta k plus 1, we compute the set of delta based on theta k and theta k plus 1 and add it to a Q. A Fisher selection method is then applied to identify S time steps that best explains delta from this Q. Then a time step sampler pi phi is trained to maximize delta, which samples time step t that is expected to achieve the largest reduction in the diffusion loss.
The table below demonstrates that our method, despite its learning-based nature, generally achieves faster convergence and better performance at each iteration compared to heuristic approaches. Moreover, our method demonstrates consistent robustness across different noise schedules. As illustrated in the figure above, our method achieves robust performance by adaptively sampling time steps throughout the training process, whereas heuristic approaches rely on fixed sampling strategies. Furthermore, the figure here shows that our method also achieves faster convergence in terms of wall clock time compared to heuristic approaches. Here, the right column of the figure illustrates the time step distribution sampled by our method when applied to DDPM. The left column illustrates the variations in gradient variance and diffusion loss observed when training DDPM using LVLB rather than LDDPM without incorporating our proposed method. Training with LVLB differs from the conventional diffusion training with LDDPM in that LVLB weights the losses across time steps differently using the constant CT. Since CT has larger values at later time steps, it leads to increased loss and gradient variance at these time steps, especially with the cosine schedule as shown in the figure. We argued that the number of iterations required for convergence would be proportional to the gradient variance at convergence, assuming independence across time steps. The time step sampling distributions shown in the plots supports this intuition, with the linear schedule heavily sampling low time steps and the cosine schedule sampling predominantly from both from low and high time steps. This suggests that the direction that most effectively reduces the original objective, LVLB, somewhat aligns with sampling time steps that exhibit higher gradient variance. Thank you.